So the negative version would be, well, I'm going to change positives to negatives all the way along. And then what we're going to do is we're going to add term by term. And you can actually see what happens is that if we listed this out, this is 1 plus x minus x plus x squared minus x squared plus x cubed minus x cubed. Effectively, what's happening is the x's, the the individual terms in the power series are telescopically cancelling all the way down. This pattern is going to continue all the way down through to infinity. And what we're left with is we're effectively left with 1. Okay, which is nice. So what we've actually done here is the difference between these two functions. The difference between them is simply equal to 1. And what do we end up with? So therefore, what do we got? What we got? Well, there's a common term here. We have g1 of x times 1 gives us g1 of x, and times minus x gives us x times g1 of x. That must be equal to 1. And therefore, we have that g1 of x is simply equal to 1 divided by 1 minus x. So let's just recap. Typically, we're familiar with working with sequences where all of the values in the sequence have been listed. And then typically we need to try to figure out whether they're arithmetic or whether they're geometric sequences. And we use the typical formulas to calculate some sort of, let's say, recursive definition for the sequence. Okay? But what we're doing here is this, is that we're going to take the sequence that's presented to us. We're going to encode it as a power series, okay? So that each term in the sequence is simply a coefficient, okay, in this particular power series. And then what we're doing in this particular case is we want to calculate the function. In other words, we want to sum up this power series. And one trick that we can use to sum up a power series is to try to figure out whether by multiplying the power series by another term, whether, or another value, another factor, whether that allows us to cancel out terms. And you can see what's that happening here. So effectively what we have here is that this particular function is the generating function. This is the generating function for that particular power series. Okay. This function is the generating function for that power series, and this power series encodes that sequence. So there's a relationship now between this sequence and this particular generating sequence. Let's do another simple example. Okay, let's consider, and I just want to show you some neat tricks. This is just an introduction. So let's consider the sequence. Let's consider the sequence. This time, let's consider the sequence 2, 2, 2, 2, all the way on to infinity. So it's very similar to the previous one, but this time each term is a 2. So it's a constant. All terms are constant all the way through. What does its power series look like? Well, let's have a look. Its power series is going to be, don't forget, each one of these represents the coefficient, okay, of a power series. So it represents the coefficient in a power series, and typically the power series would be, in general, let me just write that down. I should have really gave this at the start. In general, the power series would be C0 times x to the 0 plus C1 times x to the 1 plus C2 times x to the 2 plus all the way through to infinity, which could be encapsulated as the sum of from, let's say, from I is equal to 0 to infinity of ci x to the I. Okay? So this is the power series that all of our sequences are going to be encoded to. So in this situation here, the first term represents the first coefficient, the second term represents the second coefficient, the third term represents the third coefficient, and so on. So the power series for this particular sequence is simply, don't forget, x to the 0 is always equal to 1. So the first term is always just the first term in the power series doesn't have an x there. Okay, well, there is there, but it's x to the 0 is a 1. So the first term is going to be 2 plus the next term is 2 times x to the 1. So it's 2 times x to the 1, which is x, plus next term coefficient is also 2. So it's 2 times x squared, plus the next term will be 2 times x cubed. Okay, and so on and so forth. And once again, let this equal g of x. Let's call this our second function. Let's call this g2 of x is equal to this. Once again, let's multiply it by x. So x times g2 of x has the effect of 2 times x gives us 2x. Okay? Sorry, x times 2 gives us 2x. X times 2x gives us plus 2x squared. X times 2x squared gives us plus 2x cubed, and so on and so forth. And once again, what we'll do is we'll subtract one from the other. We'll calculate what g2 of x minus x times g2 of x is. So we're going to take these terms away from these. So we're going to subtract this positive. So these all become negative all the way down. Okay. And what we can hopefully see again is that, well, these two are going to cancel. These are going to cancel. These are going to cancel. And the pattern is going to continue. And what we're left with is a 2 here. Okay. So we're left with a 2. So this becomes 2. Once again, the common term here is g2 of x. So we take that out. g2 of x times 1 minus x gives us 2. And what have we got? So therefore, we have g2 of x. The generating function is simply equal to 2 divided by 1 minus x. Okay? So this is the generating function. Okay, for this is the generating function for this particular power series here that we defined. Okay, which encodes the sequence that we defined earlier on. I could do another one of these, but I really want to just say, okay, the next step, we could do 3, 3, 3, 3, and so on. Let's do just a common, let's say we do, so we just want to try to consider how we can calculate the power series for any constant sequence. So let's consider, and hopefully we can see that the only difference between this here and this is, oh, if we multiply g1 of x by 2, it gives us this thing here, which is effectively what has happened here. If we multiply each term by 2 here, we get this particular sequence here. So let's just show you in general. So let's consider, let's say for argument's sake that we want to consider, let me just leave this one over here. Okay, whoops. So let's consider, right?